Hello and welcome to KAUST Live. We're coming to you from the Winter Enrichment Programme. This year's theme is time. Time is one of life's most universal experiences, but how much do we really know about the physics, the cultural impact and the feeling of time? Here to speak to us about the quest to uncover the mysteries of the first black holes is Professor of Physics and Astronomy at Yale University, Priyamvada Natarajan. Professor, it's an honour. Thank you for joining us.
I'm delighted to be here.
So I'd just like to start with a question about your background and how you got into this field. So when we talk about black holes, we use evocative terms such as event horizon, singularity, supermassive. Was it the mysteries behind these terms that first captured your imagination growing up in Delhi?
Well, black holes are the most enigmatic objects in the universe. And I was drawn to them particularly because of what a black hole really is. It encases, as you mentioned, the singularity, this point where all known laws of physics break down. So at some level, black holes mark the boundary between what we know and what we don't know. So to me, that was very, very seductive. It seemed like a boundary one ought to push and to figure out the nature of the singularity, though I have ended up working not so much on the nature of the singularity itself, but the formation of black holes and the growth of black holes. And black holes that we know are ubiquitous in the universe. So for example, even our galaxy, well, most, if not all galaxies, appear to host a central black hole. And our galaxy, the Milky Way, hosts one that's about 4 million times the mass of the sun. So the fact that these objects are not as rare as we thought they were initially, and the fact that they're so enigmatic was what drew me to them.
And I've heard you liken your work to cosmic archaeology. Can you explain why?
Yeah, so because what we're really trying to do is to look out into the universe, and this is what is crazy about the universe. When you look out into the night sky, you're actually looking back in time. So you are seeing the universe as it was. So the age of the universe today is about 13.8 billion years. And so when we look out, the farther and farther we look out, the deeper we look, the farther we reach, the more we go back in time. So we access the young universe when we look out with the strongest telescopes, either in space or in the ground. So in some sense, we're looking at the younger universe and we're trying to assemble a timeline, which is very similar to what archaeologists are doing when they dig and they're trying to reconstruct what a culture was like and what the mores were. So in a very similar vein, what we're really doing is looking back in time and reconstructing the growth history and the assembly history of the universe.
And originally, black holes were conceived as mathematical solutions to Einstein's equations, and no one thought they were real.
Yeah.
What changed?
Yeah, so this is what is so fascinating about black holes. So no one believed, scientists and Einstein famously, whose equations actually had permitted this black hole solution. And it was believed that they were a mathematical curiosity because of the peculiar nature of the solution. So Einstein's equations actually relate matter and the impact of matter on space. And so the black hole solution is one of the simplest solutions. Einstein did not believe there would actually be any exact solutions. And when they found this simple solution, actually it was Carl Schwarzschild who found it, it's the shape of space around a very, very compact amount of matter, point mass almost. And so it's a very extreme curving of space around matter. And so it's an odd solution. It's a very non-intuitive solution. And of course, then there's the singularity that's encased there. And no one thought that these would correspond to anything real. They thought, oh, it's a mathematical solution. And it's, it's beautiful in the way mathematics is, in the sense that it's an incredibly sharp definition of something very complex and a representation of something very complex. But I think what really changed is when Subramaniam Chandrasekhar, who was an astrophysicist, an Indian astrophysicist who went to Cambridge to study in the 1930s, he actually worked out that the end states of stars could be such compact objects. So stars that are more massive than 8 to 10 times the mass of the sun would exhaust their nuclear fuel, they would combust, they would explode, and they would leave behind this little remnant that would be extremely compact. And that matched the description of what a black hole would be mathematically. But no one believed him, and it took a while. And it was eventually when, during World War II, people started doing simulations of explosions for other reasons, they discovered that the black hole solution was a real solution. But then it was really the discovery of objects that are compact objects in the universe, like neutron stars and pulsars, which are very fast rotating neutron stars. So discovery of pulsars, the discovery of quasars, which are growing black holes, all of this happened in the 1960s. So it was then that when people detected, so Jocelyn Bell and Anthony Huish discovered pulsars, and so it became clear that the end states, these compact end states, were actually real objects in the universe. So that suggested that black holes could also be real. And then with the discovery of quasars, it was very clear that black holes were real. So it's been a very interesting history for black holes. They were deemed unreal, then they became real, and then they were deemed very marginal because they're like, well, the end states of stars, maybe there are a few here, and so on. And now, in the last decade or so, we've realized that not only are black holes ubiquitous, black holes of all sizes inhabit the universe, they're littered throughout the universe, but also central black holes, the supermassive black holes that are more than 1 million times the mass of the sun that inhabit the centers of galaxies, seem to play a very important role in shaping galaxies, in how many stars form. They almost act like a piston and control the amount of stars that form. We're still trying to understand that relationship between the central black hole and the stars right around. So, they've kind of come center stage after being sort of, they're playing a starring role, if you will, in galaxy formation. And I think it wouldn't be a far reach to say that black holes probably structure the universe. And, no one could have imagined. Even when I was doing my PhD, we really did not know that black holes would play such a pivotal role in the formation of structure.
And Stephen Hawking, of course, hugely popularized astrophysics and black holes in particular. Can you talk in a little more detail about his contributions to the field?
Yeah, so Hawking made many significant contributions to black holes and their, in the cosmic context, what these objects really were. He worked out the physics of these objects, and he understood at a very deep level the nature of the energetics of these objects. So he came up with this understanding of the entropy of black holes. So he helped us understand and model black holes in a way that nobody had done before. People really didn't know how to deal with the singularity. And so he provided a mathematical framework and a model to think about black holes. So he worked on the entropy of black holes, related the entropy to the areas of black holes. He helped us understand the nature of the event horizon. So all black holes have this sort of sacred boundary, if you will, that's called the event horizon, and not even light can escape the event horizon. And that's because the gravity is very intense of black holes, and all matter, light, anything that crosses over never quite makes it back out. So, there's a sort of deep questions, some of which are still unsolved, and Hawking was working on them till the very end. Sort of the thermodynamics of what actually happens to matter when it crosses. So we have to understand that there's information that's coded in stuff that falls into the black hole. If that disappears into the event horizon, what does that really mean thermodynamically, right? So, and so Hawking made many important contributions to even framing the problem. It's a very difficult problem. So even setting up the problem so that you can think about solutions. And, and he also worked a lot in trying to understand the very early universe. Although black holes do not play an important role very early on, as I mentioned before, they're very important constituents. They're not dominant constituents in terms of the mass or the energy density that they contribute, but they play a very pivotal role, and they sort of pockmark space-time. So he's made a lot of contributions in sort of conceptualizing black holes, given that they're such peculiar objects.
And our common understanding is that black holes form from massive collapsed stars. But can you tell us about the other theory of the formation of the first ever black holes?
So I think the conventional way to form black hole seeds, as they're called, the first black holes, is from the remnants of the first stars. So in 2005, 2006, with one of my postdocs, Giuseppe Laudato, we actually came up with an alternative model. And that was motivated by the fact that these initial seeds that come from the first stars are really tiny. They're sort of maybe a few times to maybe 50 times the mass of the sun, depending on the mass of the initial star. And these seeds are they give a very slow start to understand the formation of the most massive black holes in the universe. And so we decided that there ought to be another way to make a very massive seed from the get-go. So a seed black hole that is 10,000, maybe 100,000 times the mass of the sun to start with. And so we figured out that there are particular, very specific conditions in the early universe that would actually permit you to do that. So all you need to do is to form a very massive gas disk that could go unstable in a very particular way without fragmenting. It would just sort of flow in. It would have an instability that would set up a flow. It's rather like your bathtub. When you pull the plug in your bathtub and you see the water really, see this vortex and your water's swiveling right in. So you have the same kind of thing early on in the universe with gas. And then it forms, ends up going to the center and forming this object that we call a direct collapse black hole. So this is an alternative model. And when we first came up with the model, everyone thought, oh, this is very speculative. But then increasingly, as computer simulations have gotten more sophisticated, we've been able to simulate this. And it appears that there are regions in the universe where this could happen naturally, given sort of our current understanding of how galaxies and structure forms, that there's room for this kind of model. And we don't think this is the dominant way to make all black holes. We still think that the stellar mass remnant black holes are probably the majority of the seeds. But to explain the most massive black holes in the universe, the earliest quasars, you really do need another channel. And I think what has been exciting is that this other channel, direct collapse black hole, stands to be tested very soon with the James Webb Space Telescope. So we're really, really excited.
And how significant has the discovery of gravitational waves been to your work?
Well, it's one of the major discoveries of the 21st century. I mean, there's no question about that. They've been predicted, and we've been looking for them. But, super exciting that the LIGO collaboration detected gravitational waves. We knew that gravitational waves had to be there because we had other indirect evidence. But the direct detection was really amazing. However, I'm, of course, more interested in the obese cousins of these supermassive. I'm interested in the supermassive black holes. And they collide, too. But the frequency at which you would be able to detect their collisions is much lower than the LIGO black holes, the stellar mass black holes. So we have to wait for the LIGO type of apparatus to be put in space. And the Europeans have a mission called LISA, which is due to launch in the late 2020s, early 2030s, that should detect the gravitational waves that are produced when two supermassive black holes crash into each other. So I think for me, that would be an incredible discovery. And it's pretty clear that that must happen. So the LIGO collaboration and the detection of gravitational waves from the collisions of lower mass black holes is suggestive that, this should occur. And I think in our understanding of how black holes grow, they do grow by colliding with each other, too. It's not the dominant method by which they grow, but they do grow by colliding. And in the early universe, you expect to have been a lot of collisions to have been shaping how black holes grow.
And what discoveries in cosmology are you itching for us to make next?
So I think one When I look at the longer term, it's definitely the gravitational waves from supermassive black hole collisions by LISA. But I think there's a discovery that I'm super excited about that is due to be announced in a couple of months. So this is a very clever experiment called the Event Horizon Telescope, where basically they have leveraged radio telescopes on the Earth at various locations so that the entire surface of the Earth acts as a radio dish, as one antenna. So it's a dish as big as the surface of the Earth. And what that allows you to do, it allows you to get very close and map right around the event horizon of the black hole in the center of the Milky Way. So right outside the event horizon, there's a radius called the Photon Radius, which is a radius where light at that radius would be captured and you'd see a shadow. And this is, it'll be there forever, so you see the silhouette, if you will, around. And this experiment will be imaging that for the first time. And so that's as close in to the event horizon as we will ever get to a black hole. And it is also as close in to test the strong gravity that is predicted for black holes. There are these immense sources of gravity. And so I think we'll be mapping the intense gravitational field really up close for a black hole. It's never been done before. And it's an image. So, I think for me, one of the other interesting things about the topics that I work on, dark matter, black holes, is that these are invisible entities. So you never directly see them. And so you only have to infer their presence and what they do in the universe from their vicinity, their impact on their vicinity. And so, this is getting really close to a black hole. The collaboration has all the results in the can. They took data over the last 2 years. And I think we expect this image, this sort of shadow, anytime in the next couple of months. So watch that space. So that's something I'm very excited about vis-a-vis black holes. And I think, in cosmology in general, I think it would be awesome if in my lifetime we unravel the nature of dark matter. I think there are all kinds of experiments, both, collider experiments, direct detection experiments, indirect detection from astrophysical phenomena, from sort of impact on surroundings. So I think it would be really cool if we detected the particle. And I mean, it is a hard problem, and I think a lot of people get impatient with it. But, the LIGO people were looking for 40 years before. So you never know. It may be just around the corner, and or we may be looking in the dark, so to say. And we may need to, reconsider our strategies. I think we're constantly doing that because we've been looking for about 20, 25 years. And we've ruled out bits of parameter space, if you will, so properties, potential properties for what the dark matter particle can be. And, the leading candidate, the most persuasive candidate that sort of fits in with everything else that dark matter needs to accomplish in our universe are these neutralinos, these weakly interacting massive particles called WIMPs. But we've not really seen them. So I think, we've been, in the last 5 years or so, people have been reconsidering other classes of particles, lighter particles like axions and particles that are probably made at a slightly different time in the universe. Will still solve the dark matter problem, and of course, it may turn out that in the end, dark matter may not be just one kind of particle. The simplest option is that it's one kind of particle, but it could be many kinds of things constitute dark matter. I often joke and say it could also be my unmatched socks. Every time I do laundry, I seem to be missing socks. I'm always joking that maybe my unmatched socks constitute dark matter, a small portion of dark matter. But it would be nice if it was not a conglomerate of many, many kinds of particles. It would be cool if it was a simple, but there's no reason nature ought to be that simple.
Okay, that would seem to be a good point to see if there's anyone in the audience that wants to ask a question. No? Okay, well, we'll look to Facebook instead. The question is, black holes in themselves are so fascinating as a field. Why then be drawn to dark matter as well?
No, but I mean, they're similar, right, in many ways. They're both invisible entities, and they are very, very significant. Well, dark matter is significant because it is the dominant component of matter in the universe. The stuff that we're made of, all the ordinary atoms, everything in the periodic table is barely 4%, 5%. So dark matter is clearly a key player in the universe. So obviously one wants to work on a problem where we know that this is a very important entity in the universe. And I think for me the draw has always been this sort of this boundary between knowing and not knowing, and sort of not being able to directly see it. So it's sort of like it's pretty much like a detective story where you're really trying to figure out. And so I think for me the appeal is actually very similar. And even dark energy that I worked on. So all these entities are these invisible, elusive kind of entities. I find very, very exciting. And I think also what I find exciting about these kinds of problems is that there's room for a lot of speculative intellectual risks, and I like that. I like sort of coming up with ideas, new kinds of ideas, like this idea of direct collapse black holes. And what's exciting right now, I feel very fortunate to be doing science now, right, is that you can propose an idea and it can be tested and either ruled in or ruled out within a lifetime, and much shorter than a lifetime. So the idea of direct collapse black holes, proposed in 2005-06, stands to be tested in another couple of years. So I think that to me is really exciting. It's that process that excites me. And so a lot of these problems that I work on have that possibility lurking, because they have been so challenging that there have been a lot of ideas out there, and then people are actually actively testing those ideas.
Thank you so much for your time, Priya. I think your keynote's clearly going to be fascinating.
Thank you very much. Yeah.
That's all the time we have for now, but join us again at 3 p.m. today as we speak to John Ellis about the Large Hadron Collider and how it may allow us to answer fundamental questions about the universe. Remember to comment, like and share on all the KAUST social channels using the hashtag WEP2019. And for everyone here at KAUST, thanks for watching.
And thank you so much.